Right. Cool. Hey everyone, thank you so much for joining. People who have joined in virtually as well. So I'll be presenting our work on a novel algorithm for full resolution registration of gigapixel images with sub-cellular accuracy. So I work with Dr. Shikhar Uttam and his collaborators. First things first, why do we even need this? So tumor microenvironment is pretty complex with a lot of types of cells, their interactions as well as interactions of the cells with the surrounding extracellular matrix. But typically it is studied in a very narrow sense. So the current methods just look at a very small sliver of the complete picture, but this is the actual complete picture. So this gives us the functional as well as architectural or slash morphological view of the environment. There have been a lot of efforts in the recent past to be able to study tumor microenvironment in a 3D context as well as in a 3D context. But the 2 points that I would like to make is we need 3D reconstruction as well as at a cellular resolution. So I would just like to go over this method. So this is what we would expect from a 3D reconstructed tissue sample. So this was an example of a current state-of-the-art method which does 3D reconstruction from serial sections of H&E stained tissue images. This does a great job. And, yeah. So what it's doing is it's aligning the serial sections of images. I think it's not moving forward. How did that go forward?
Probably crashed briefly. Do you have like a video or something?
No, it's just an animation.
Strange. That's not good. Are we here?
Yeah.
My guess is it's probably like the videos because this computer's kind of slow.
Oh, I can skip to the next one then.
Okay, well, it's not cooperating at all, right? So, could you present it like this, maybe?
Yeah, that works. Yeah.
Okay.
Okay.
Okay. So it's up there only now.
Oh, so I'll have to look there and present?
Well, it's the only thing that's working.
Oh, okay. Yeah, I think I'll just go with that. Yeah.
What slide?
Yeah, the sixth one. Yeah,
very slow. But yeah.
I made sure to not add gigapixel images, but
Okay, let's try it like this.
okay. Yeah, so what I just showed the video, that's reconstructing the tumor microenvironment from single sections of images. So this is how the images look like when they are acquired and overlaid on top of each other. They are completely misaligned. And yeah, so the current methods face with two fundamental issues. One is resolution and scalability. And I think I'll be the fifth one talking today, saying that not everyone has good huge compute power. So here we go. So the it's something before this.
This.
It was like an animation, so there's an image just behind
so
this.
that's not going to work, probably.
Okay, so let's imagine that there's an image right behind this, which is actually downsampled. So the image at this resolution is very huge, and like each image is about millions of pixels at least. So imagine aligning at least 300 sections together. It's a humongous task. So the current methods downsample them, and that leads to loss of a lot of cellular level information. We are able to align the images at the native resolution at which they are acquired. Okay. Okay, so then
Which side do you want? 8?
the next one.
Yeah, just press it once and then don't press it again.
Yeah, this is the other issue, which is so registration or alignment is as a problem has a trade-off wherein you want to align but not completely align them because the two sections are fundamentally different. So you don't want to be forcefully aligning two images completely. So the current methods, when they actually try to align them, they need to distortion, and when we 3D reconstruct it, that's going to give us a very wrong picture. So this is one region where you can see there's a significant region where there's a significant distortion. So now we move to our method, but which I'll need to show the animation.
You can try to
Okay.
put it. Should we try? I mean, it almost crashed last time, but.
So yeah, just going with it. So the typical workflow is we have serial sections, and each image is without any processing about it is of the size of millions of pixels, but we calculate its contours that reduces the number of data points to just tens of thousands, and then we align them at two levels. One is coarse alignment, which is pretty fast, and that is the scalable part. And next is the finer alignment, which helps us which helps us 3D reconstruct at a cellular level. So here we show the difference between the current method and the method that we worked on, wherein the current method has, due to downsampling, leads to a lot of missing information, whereas we able to reconstruct at the resolution or the resolution at which the images were acquired at. So this is an example of two images which are overlaid. So let's suppose the first section, the second section. So this is what we see after they are overlaid, and using our method, we can see a cellular or a nuclear level registration. So fundamentally, there were two issues with the method. One is the resolution and scalability, which we solved by calculating the contours. And second was with respect to the tissue image being distorted. And as we see, there's very minimal distortion using SPARIC. Yeah. So this is a comparison of SPARIC with CODA on three performance metrics, where which is target registration error. So there's a publicly available data set which most of the registration algorithms compare to. And there are fusion markers, and they calculate the error between each pair that is accumulated across the whole section. As we see, the error using SPARIC is much lower than that we get with CODA, as well as the change in area is lower as well, which emphasizes the fact that it leads to very minimal distortion.